Hello and welcome to another one of D's ADD videos. Today we're going to be looking at the concept of area of surface of revolution. Anytime we take a curve or a line and rotate it about an axis, there's going to be a volume associated with that three-dimensional object that we create and also a surface area. And depending on what form the function we're given is in, and the axis of rotation, there are different formulas for the area. So let's look at what I'm talking about. The basic concept is we have a curve, or a straight line in this case, and we look at a specific region. So x values are going to be from 0 to 2. Y values are going to be 0 to 4. You might say that this distance is twice as long. Well, let's say the y-axis is in units of 2 and not 1 like the x-axis. Okay? No need to be that picky. We're trying to learn a different concept here. So when we rotate that portion around the x-axis, for instance, we get a three-dimensional shape, this cone-looking structure. And what we're looking for is the lateral surface area, not the circle base here that you see, but the slightly darker area that we've created, surface area. All right? So again, the main concept is, what am I rotating about? Am I rotating about the x-axis? If that's the case, then this is what I have to memorize. I'm going to have the basic form of 2 pi y times the square root of 1 plus the derivative squared dx. Okay? So that's the basic thing. If we're given f of x, not y, for instance, like if this was y, here you see the y, dy dx squared dx. And then here, if we're given f of x, well, f of x is a synonym for y. They're interchangeable. So everywhere you would see a y, you would plug in an f of x, and everywhere you see a dy dx, you can plug in an f prime. Now, sometimes we do rotate about the x-axis. However, our function is given to us in the form of x equals. So in that scenario, what we need to do is plug into this bottom formula here. Okay, so it's usually 2 pi y, or f of x, which are synonymous, but sometimes we can't do that. So we opt to use this formula of 2 pi x 1 plus dx dy squared. All right? Your natural inclination might be to solve for y and plug in, but no, just use this formula. Notice that the bounds have changed. We're looking at the y values now of c to d because we're integrating with respect to y. Whereas here, a to b because we're integrating with respect to x. All right? So 2 pi y integral of this differential right here element ds that a lot of textbooks use. All right. So what happens if I rotate it about the y-axis? Well, if I rotate it about the y-axis, your shape would change if we were looking at another example, but your formulas would also change. So the general form here is 2 pi x square root of 1 plus dx dy squared, and because we're rotating about the y-axis, it's a dy. But if your function is given to you in the form of y equals, then it's going to be 2 pi y, the square root of 1 plus dy dx squared. All right? That's the general concept. It's a lot of memorization of formulas and when to apply them. If you do enough of these examples, they'll come second nature, and you'll be able to just do these pretty easily. If you just think you can rely on the formula and plugging in, a lot of this is a test of your integration. These are applications of integration, so you will come up with not only a challenge in knowing what formula to use, but also how do I integrate the resulting problem. So I recommend you just do a bunch of these, and then I think you should be good to go. I hope I've clarified any doubts that you might have. Practice, practice, practice. Thank you, and have a nice day.